Today's lesson is going to be about electric potential, or in other words, voltage. Okay. First off, we're going to define what electric potential and voltage is, okay, and how do we calculate it? And again, like with a lot of this stuff with electricity, we need a way to visualize this, and then we're going to use that electric potential to calculate work. Okay, so to begin with, okay, when we analyzed electric force, we looked at the force between two charges. And then we moved to electric field where we just looked at one charge and the field generated by that one charge. Okay. Then we moved on to electric potential energy where we looked at the energy stored with two charges held in position. So like a rubber band or a spring, there's energy associated with that when we move them farther apart or bring them closer together. Okay, now with electric potential, okay, or another term for electric potential is voltage. This is the voltage generated by a single charge. Okay, so the way we said with force to field, one charge generates a field of, fills the space around it with electric potential. Okay, and then when I do put a charge there, now we can calculate energy or work as that charge moves around in that electric field. Okay, so I use the terms electric potential and voltage almost interchangeably, okay, because they're pretty much synonymous. Going forward, I'll pretty much use the term voltage in the next unit and almost all units after this. Okay, most of the time we're going to be looking at the voltage difference between 2 points, from point A to point B. How much has that voltage changed? Obviously, the units for electric potential will be volts, and the formula for it is given below as voltage is equal to K, that 9 times 10 to the 9th we've been working with, times the charge Q divided by R. So just like we went from Q over R squared for force, down to KQ over R squared for field, we get rid of a Q again to go from KQQ over R for potential energy, and then we divide by little q and get K capital Q over R for voltage. Okay, now electric potential or voltage is a scalar, so the sign of the charge generating the voltage field is important. Okay, so in this case, it is possible to have a negative voltage. We're not going to be looking at directions because voltage is a scalar. Okay, and so by definition, when we look at this formula, okay, when the distance is basically infinity, the voltage or electric potential is going to be 0. Okay, and so electric potential energy is also 0 joules when the two charges are separated by a distance of infinity. Okay, now to visualize electric potential, we use a concept called equipotential lines. Okay, for a point charge, the electric potential is equal when the distance r from the point charge is equal. Because if we look at that formula, K is a constant and Q is a constant. The only thing that changes is r. So for a point charge, as long as we're the same distance r from that center, it's going to be the same voltage. And so we end up with these concentric circles that we see down below. Okay, and each one of those circles, there's no direction associated with it again. Remember, because equipotential is a scalar. So it's just, you know, this line making a concentric circle. Okay, as these lines move farther away from the center charge, okay, the distance between the lines must increase. Okay, so for a positive charge, the lines decrease in value as they move away. So it starts at 100, close to the positive charge, then 90, then 80, 70, etc. For a negative charge, the lines increase as they move away. They approach 0 in both cases. So in the negative charge case, it would start at the closest one as minus 100, then minus 90, then minus 80. Okay? So equipotential lines are similar to something that some of you who may hike have seen before. Okay, hikers are the ones that see these kinds of maps the most. Okay, they're called topographical maps. Okay, because electricity and gravity have a lot of things in common. Okay, so when we talk about topographical maps and gravity, everything at the same altitude, okay, if I drop the marble or drop the mass at that point, okay, it has so much potential energy at that altitude. By the time it gets to zero level, they'll all have the same kinetic energy. Okay, so if I then take that analogy and extrapolate it to electricity, okay, anywhere that has the same electric potential, so in the lower right hand corner, we see things like 2 kilovolts, 1 kilovolts, -2. Okay, things that are below zero are kind of like, okay, they're underwater or in a valley or something like that. But that's okay. Okay, everything on that line, if I move from one line to another line, I know how much altitude or how much change in voltage I've had. Okay, and again, similar to topographical maps, okay, when the equipotential lines or the altitude lines are clustered tightly together, it kind of means that the gravitational field there is stronger, or the electric field is stronger, because I'm going through multiple lines in a very short distance. Okay, so how do I draw equipotential lines when I have electric field, or vice versa? Okay, and basically there's two rules associated with equipotential lines and electric fields. The first rule is that equipotential lines are always drawn perpendicular to the electric field. Okay, so electric field is perpendicular to the equipotential line, and the equipotential line is perpendicular to it. Okay, and that gives me more or less the direction, but there's still two directions. Okay, so even for like this point where the X is, okay, my electric field is perpendicular to that, but I don't know really if it points to the right or to the left. Okay, and that's where the second rule comes in. That second rule says that the electric field always points in the direction of decreasing voltage. Now this line here is the 30 volt line, and this line is the 10 volt line. Okay, so I can see that if I was to draw a direction, right is probably much more appropriate. Okay, and so the electric field always goes in the direction of decreasing voltage. If for some reason, okay, this was a -30 and a -10, then yes, okay, decreasing voltage would point this way. Okay, but right now they're +30 and +10, and so it points to the right. Don't forget the perpendicular. If I was over here, it would be slightly more inclined. Okay, so when I have a uniform electric field, okay, remember, two parallel plates, one positive, one negative, create a uniform electric field in between the two plates. And so equipotential lines are going to be parallel to those plates because my electric field is just up and down in this case. So my equipotential lines are going to look like this, okay, where let's say this was, if this plate was at 100 volts, then this would be at 75 volts, and then this could be 50 volts, and I would have another one in here for 25 volts, and then 0 volts. Okay, so again, perpendicular and pointing in the direction of decreasing voltage. Now there's a formula here that tells me how to calculate the voltage or electric field given some characteristics. The characteristic that we're missing is that the D is the separation between my two plates. How far apart are these two plates? Okay, and so if I know the voltage, in this case 100, between the two plates, I can calculate the electric field as long as I know the spacing. Okay, if the spacing changes, then my electric field changes. Okay, so calculating electric potential from multiple charges, okay, just like we've been doing with force in the field and the potential energy, okay, we're going to simply be adding my potentials. Okay, so if I calculate the potential from one charge at a specific point and the potential from the second and the third and as many as we have, okay, and I add all those potentials together, I'll get the net electric potential at a point. But remember, okay, electric potential is a scalar. So if the charge was a negative charge, my electric potential would be a negative electric potential. So it is possible in this case that some of my numbers are going to be negative, but I'm still going to be adding those numbers. Okay, and so it is possible also to have a net voltage of 0. Okay, so here's an example of how we do this. Okay, I have a positive charge located at Q1 and another positive charge a negative charge located at Q2. Okay, and so in this case, I want to calculate the net electric potential, not at the origin, just to change things up a little, but at point x equals -2. So that's this point here. Okay, and so from the first charge, this distance is 6. So that's where this number comes in. And I just put K, Q1, 5 millicoulombs, 5 times 10 to the -3. Multiply that all out, and I find that the electric potential from that charge alone is 7.5 times 10 to the 6 volts. For the second charge, again, it's KQ. In this case, my distance is 5. And so that's where this distance comes from. And I keep the minus sign here, okay, because it's going to be important. So keeping that minus sign and plugging it into my calculator, I have a voltage from the second charge of -4.5 times 10 to the 6. Either way, I'm going to add these numbers, okay, positive, negative, or whatever. Okay, so when I add them, I find at that point, x equals -2, I basically have a net electric potential of 3 times 10 to the 6 volts. Okay? So I talked earlier about work and moving a charge around the field. Okay, so when I take a charge and it actually moves from one point to another, the equipotential lines in that visualization helps us out because we can now calculate how much work was done on that charge. And remember, work is change in kinetic energy, and kinetic energy is the useful energy. Okay, so using that formula, we find that work in electricity has a formula of -Q times delta V. Now for this class, we're not really going to get into the details of why it's -Q delta V. So we're pretty much going to stick with positive works only. Okay, so don't be overly concerned about that minus sign there. Okay, and I will frequently just use it as Q delta V. Okay, but anyway, as a charge moves from voltage A to voltage B, okay, the electric field is doing work. Okay, it's making that charge move faster usually. Okay, and so as it moves faster, it gains kinetic energy. Okay. So we're going to be doing practice on these things, okay, and that's what the homework package talks about, okay, and being able to then calculate how fast those charges are moving, because remember, kinetic energy, that also equals 1/2 mv squared, okay. So thank you, bye-bye.